Okay, so we need to finish the slides from last time, and then we have the slides to get through preparing for the lab today. So we can do this question together. We don't need to do this as a poll. So unlike the Mealy machine, this one is a Moore machine. So the combinational logic blocks are going to be doing different things. So the question is asking about C2. So remember, for the Mealy machine, the output depends on both the current states and the current inputs, right? But for a Moore machine, the output only depends on the current state, right? So last time we answered B, right? Input, state, output. But now we don't have input as part of the input into this combinational logic block, right? It just has current state. And then the output is the output. So we only need current states, outputs for a Moore machine in order to implement this logic. Is that clear? All right. So here is our state table for the Moore machine. So just like with the Mealy, I have the states. Oh, here, let me again switch. So the states, I give them names. And then if I'm in this state and my input is 0, I'm going to go, well, if I'm in this state, my input is 0, I go to this state, and this is my output. And this output, again, only depends on current state. That's why if you look here, S0, 0, 0, S1, 0, 0, S2, 0, 0, S3, 1, 1. It doesn't depend on the input. The only thing that depends on the input is what is the next state going to be, right? So like here for S0, if it's a 0, I go S1. If it's a 1, I stay in S0. And then once we have this table, which is just the translation of this diagram, right? We can give the states their binary encodings, right? So 0, 0 represents S0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. And then we just translate all of those to the binary encoding as well. And once we have this state table, we can create the excitation table for the Moore machine, right? So we have 3 inputs, the current state and the input, and then we have what's the next state, what's the output. And the output for the Moore machines, you can create a separate truth table in order to do them without the inputs, because it only depends on the state, right? Yeah. Yeah, the output only depends on the state. So the state table is in this format, where it has the current state, and then what is the next state, comma, what is the output. And then the excitation table is just in more of a truth table format, so that when you go from the excitation table, you can go directly to the K-map. Because we know that 0 corresponds to the 0 box in the K-map. But to go from here to the K-map, you basically should draw this first. Okay. So the excitation table is just made to make going to the K-map easier. But all three of these things hold the same information. All right, so here is our K-maps, right? So this is for the most significant bit. We would circle here, and we would circle this. And then for D0, we have these three little circles. And then for Y, you have this one circle. Right. All right. So let's actually do these then. I need my pen. I'm circling this and this. This one is these three little circles. And then this one is this circle, right? So D1 of t, my equation is going to be what? So for 2, I have Q1, Q0, and then I have X. And to make 2, what do I need? Q1. And then I have here my other essential prime implicant. What is changing? X is changing. And then what is Q1? What is Q0? They're both 1, right? Wait. Q0 is what? And then Q1 is 1. So this is, yeah.
Is the way that the X and the Q's around the K map, is that significant or is that just another way to write it?
Yeah, so this is
It's basically just
where we have on the top here, we have Q1, Q0, and X. Yeah. So the way that it is, sometimes it'll be drawn like this. That just means that Q0 is 1 here. And where it's not drawn the line over, that's where Q0 is 0. So then the same thing for X, right? So this is 1, this is 0. All right, so D0 of t, I need 0, so Q1, Q0, X, all not. I need to make a 5, 1, Q0, X, nope. Right? And then I need to make a 6, Q1, Q0, X. Right? And then for Y of t, it is just Q1, Q0. Right? So then to draw this circuit, Y of t is already here. It's done for me, right? So I just need to do the circuits for D0 and D1. So let's do D1 first. So I need Q1, Q0, X. So Q1, Q0, X, and then Q1, Q0. What do I need for my first one? Not. My second one was Q0 not. Okay. So I have 1, 2, 3. They should all go into this AND gate. And then here, these two go into this AND gate. And then I just need an OR gate for here. And this is D1. Right? D0 have a little bit more. Q1, Q0, X, Q0, X. And then let's do Q1, Q0, X. This is going to be 1 AND gate, 2, 3. Not. And then 5 and 6. So that's 5, that's 6. 1, 2, 3. 1, 2, 3. 1, 2, 3. And again, into an OR gate. And then connected to D0. And this is my Boolean logic circuit to implement that finite state machine. I have my 2 bits. I have the C2 circuit to calculate the outputs. And I have the C1 circuit to calculate the next states. Make sense? Okay. So we're going to cover another example of finite state machines. So this could be like a vending machine. And it's what we want is 15 cents, and you get to select which candy you want from the vending machine. So initially we're at 0, right? If we cover the Moore machine first. And our vending machine can accept a nickel or a dime. If I get no nickel, no dime, right, I stay in 0 cents. And I output 0. They can't have a candy yet. If I get a nickel, I transition to 5 cents. That's still not 15 cents, right? So they don't get any candy. And then if I'm in 0 cents, I get a dime, I go to 10 cents. Right? And again, that's not 15 yet. So I still output 0. And then if I'm in 5 cents, I get nothing, I stay in 5 cents because my customer has already paid 5 cents, right? But if I get a nickel, I go to 10. If I get a dime, I go to 15. Right? And then 5 plus 10 is 15. So then once I'm in 15, then I can say the customer can select which candy they want. Right? So that's why output is 1. And then if I'm in 10, I get a nickel or a dime. I go to 15. And they can select their candy. But remember, this is nickel or dime. So even though it's 20 cents, this Moore machine only remembers up to 15. So they can have their candy, but they don't get any change back. If you wanted them to get change back, you would need another state, right? For 20. And then you would have another output, right? So you would have an output for, are they able to select their candy? And then do they need a nickel back? And then here is the Mealy machine for the same thing. So this means I've seen no cash input. If I get a nickel, I'm still outputting 0. I get 5 cents. If I get a dime, I go to 10 cents. Again, still outputting 0. And then if I'm in 10 cents, if I get a nickel or a dime, I output 1 and I go to 15. Okay. So you can see that it's implementing the same thing. And then if you were to make the k-maps for this, you have 4 variables this time. So you have the 2 state variable, 2 state bits, and then you have nickel and dime as inputs. So that's why it's this larger k-map. So we have one for Q0, No, this one is for D1, D0, and then this one is for our output of did they put in 15 cents or not. And once you have those, you could again create the Boolean logic circuit, draw it, implement it. Okay. And do the same thing for the mealy. But in summary, we have the memory circuits that we're using, and we're using registers, right? Which are basically D flip-flops. What you need to do to design a finite state machine is first create the finite state machine diagram. So that's with the state circles, the transitions, the outputs. And then once you have the diagram, you create the state table, assign the states their binary encodings, create the excitation table, and then implement the combinational logic circuits for calculating what is my output and also calculating what are my next state bits. And then we have the mealy versus Moore, right? Does my output depend on input or not? So we have already talked about how flip-flops have these non-ideal properties. You have to make sure that you are satisfying the time constraints for setup and hold time. And you are going to do that with creating what is the maximum operating frequency of your circuits, as well as you might add buffers in order to satisfy those hold times. And then you should also satisfy if you have any clock skew that you're expecting in your circuit. Okay. So we'll cover some more examples of how to do the timing equations on Friday. And your quiz next week will be on the sequential logic and sequential logic timing. It will not be on finite state machines. Finite state machine quiz will be the next quiz. Okay. But just remember that the timing equations are important for finite state machines still too. Okay. I have register outputs into some combinational logic, back into register. I have to satisfy the setup and hold time here. Going through combinational logic circuit 1. Combinational logic circuit 2 is not as important, right? It just goes to outputs. Why? It's not going into a register. All right, so that is the slides for the introduction to finite state machines. Yeah.
Real quick for the combinational logic slide, is there supposed to be a part where Q loops back in?
Yeah, so it would go from here to over here,
Oh,
and they would have those inverters if they needed them.
okay.
But because we have it labeled here,
You
it's
just assume that.
Yeah,
it's about
yeah.
that.
all right. So let's go over your lab then. So that is lecture 16. And your poll code for today is 767. So just answer anything. We don't have a question to cover today. Okay. So your lab today is going to cover registers and counters. So registers are just multi-bit flip-flops, right? And then a counter is just using registers in order to increment the counter. All right. So the first thing that you're going to make is the synchronous reset register. So this is loading an input into a register at the positive edge of clock if the load flag is 1. And then it resets the register to 0 if the reset flag is 1 at the positive edge of the clock. So this is going to take priority. The reset flag is going to take priority over the load flag. So all that means is in the if statement, reset is first. And then otherwise, it's going to keep the current value in the register. So we cover this part by if both of these things are false, then that means it holds the value. So here is our entity declaration. We have clock, reset, load, and then we have D, our input, is going to be 3 down to 0. So it's 4 bits. And then we have Q, the output's also 4 bits. Okay? So because it's multi-bit, that's what makes it a register and not just one flip-flop. So if we have our process and it depends on clock, that's in the sensitivity list. Then we have rising edge clock. So this is what makes it synchronous. Okay, so it's this rising edge clock. So now at the positive edge of clock, if reset is 1, Q is set to 0. If reset is 0 and load is 1, Q becomes D, which is on the inputs. And then if reset is 0 and load is 0, then you just hold the value. Okay. So here's our test bench. So this is clock. This first one is reset. This is load. This is D. This is Q. So here, if we have pause edge clock and load is 1. Well, here, let's just go to this pause edge clock first, right? Pause edge clock. Reset is 0, load is 0, D is 5, but Q does not change. It just holds what it previously was, right? And it does that for 1 clock cycle and then another clock cycle. But then at this pause edge clock, reset is 0, load is 1, so Q turns into 5, right? And then it holds that value of 5 until we get to this pause edge clock. We have load again. And now we're going to load in 9. And that's why it changes to 9 for 1, 2 clock cycles. Because this clock cycle, it's pause edge clock, but 0, 0 means we hold what our value is, which is 9. But then on this pause edge clock, I have reset is 1, load is 0. So I forgot to change this again. I was testing something on this, but it should change to 0. So that's why you put the Q as 0 there, right? So I just had Q as 1. All right, but then on this pause edge of clock, we have reset is 1, load is 1. But again, reset takes priority over load, so that's why it stayed as 0, right? And it's not until we get to this pause edge clock, reset is 0, load is 1, so we load in the 9 again. Yeah.
And it's higher priority because it's if statements first.
Yeah.
Okay.
So if we want to connect these things, it's because it's first. So if you wanted load to be higher priority, you would just swap that. But the description from the lab is that reset should be the priority. All right. So the asynchronous reset register is a little bit different. Just like the previous one, if the load flag is 1, it's going to load the inputs into the register. And reset is still going to take priority over load. But the difference here is that as soon as the reset flag is 1, our output should change to 0. We did not depend on clock. So it's just like the asynchronous reset from the previous lab, but now rather than 1 bit flip-flop, it's a multi-bit register. Okay. So again, this is clock, this is reset, this is load, this is D, this is Q. So clock, reset, load, D, Q, async down here, sync up here. Right, this one is synchronous because when we get reset, it doesn't change until pause edge clock, even though reset's changed here. Okay. But for this one, reset changes here. It's not pause edge clock. Output changes immediately to 0. It doesn't wait until this pause edge clock. Okay. So again, you're going to achieve this by rearranging these if statements. Right. And if you did the extra credit for the previous lab, you already have the templates for this. But even if you didn't do the previous lab, you have a template from this, from the slides for the previous lab to help you with that extra credit, right? The only thing that you're changing is that you now have 4 bits. Yeah. The last slide from the slides helping you with the previous lab. All right. So I'm not providing you with this code. You have to write this code. Right? The other thing is you can notice that I use the same exact test bench for both of these. So you can reuse the test bench because they have the same input output. The behavior is just different. So when you create the new project to make your asynchronous reset register, you can copy paste the file for your test bench into that new project and reuse it. You just need to rename the entity that is being called in the tester file, the test bench file. All right, so the last thing that you are going to do is you're going to implement this down counter. So this down counter has clock in order to count, right? And then it has clear. When clear is 1, output changes to 0. So it clears it to 0. And then if you load, so load is here. If it's pause edge, you would load in whatever your input is. And then if you enable, that's when you start counting down. Okay. Oh. So we can see here, our current value is 10. And then when we're enabled, we count down to 9. Next pause edge, 8, 7, 6, 5, 4, 3, 2, 1. And then here is 0. And the other thing that you need to do is when output is 0, well, when the counter is 0, you need to output 1. So that just indicates that your countdown is done, right? And then here we can see that it's disabled, so enable is 0, and that's why we can see it goes from 9 to staying as 9. So again, you're going to be doing this with behavioral code. You don't have to, but it will be easier if you do.
Is that a do while loop? Or is it not?
It's still just going to be process if statements.
Okay. Oh, okay.
So it's just if I'm enabled, my
And on 8, go to 7.
no, just decrement.
Okay.
Right? Output becomes output like this one.
Okay.
400 nanoseconds, the output is 1. Is the one above it 0?
Here. Like every time it's 0, output is 1.
How does it go from 9 to 0? 9, then it's one number, then it goes to 0, or am I seeing for the last output?
Over here.
It's the one, it's the output next to the circle one.
Next to the circle. You mean 0 to 10?
The last of it, it's in the output waveform. It's when it hits 1 at the end. Is the number above that 0?
Okay, here.
Yeah. You output 1 when data is 0.
I can't change the laser pointer. All right. Let me just go up here. I don't understand the question. Where?
It's someone next to it?
This one?
No, when the output is 1 right before the end.
This one.
Yeah, is the number above a 0?
Yeah.
So how does it go from 9, then it's one number, then 0?
So it goes from 8 to 0 because we clear.
Oh,
Clear. So again, I am not providing you with a whole bunch of the code here. Just do use process blocks. And it can be helpful to have one process block to handle the counter, one process block to handle the output. You can put them both in the same process block. But going back to our previous slides, like with the finite state machine, you have combinational logic block C1 to handle what is the next state. And then you have combinational logic block C2, which handles the outputs, right? So it can be useful to separate these two things. All right, the other thing is, in order to be able to use the subtraction operator, you have to import the math library. If you don't import it, then you can't use subtraction. So you do want to import that. Is there any questions on the functionality of this down counter? We understand the two process blocks that you would be making, and that we're going to use behavioral coding. Yep.
For the decrement, it's minus the variable, or is it just minus?
-1.
Oh,
Question?
how does it, how do you, how does it know to go back to 10 when it reaches 0? Is that another,
So if you, it depends on how you're handling it. But if you just decrement, it'll go to 15. Because when you subtract, you have 4 bits. If I'm 0 and I'm unsigned, right? And I subtract 1, then I loop back around to the top, which would be 15. So if you want to handle that, you would have a different if statement to make it 10 if you wanted it to loop back to 10. So rather than decrementing, I just assign 10, right? Anything else? You guys are all ready for this lab? So it's not too much different from the last lab, right? And then the lab after this, I believe, is going to be finite state machines. So that one will be a little bit harder. Okay, so if you guys don't have any questions, we can end. I will still be here. And I will also be in my office if you want to come to my office.